So our next speaker for this evening is Pedersen, speaking on Everettian quantum mechanics and the problem of ontological extravagance.
Okay. So Everettian quantum mechanics is polarizing. On one hand, proponents of EQM claim to have solved the measurement problem without having to invoke a collapse postulate or any hidden variables. On the other hand, the most common interpretation of Everett's formalism involves a rather off-putting commitment to many worlds. Curiously, though, many of the other distasteful features of EQM, such as issues relating to identity, probability, and confirmation, have themselves inspired vast literatures. Yet, the problem of ontological extravagance has largely remained neglected. So it's not that nobody has weighed in on EQM's problem of ontological extravagance. Albert refers to talk of many worlds as vulgar. Mark Children writes, quote, "It nevertheless appears that the more extravagant understanding, namely that of many worlds, is one whose basic ontology is clearest and which provides the logically sharpest solution to the measurement problem." Malia and Franklin separately gesture toward the extravagance of EQM as a major drawback, and Emery cautions of the costs associated with a many worlds ontology. Criticizing the formulation of EQM put forth by Deutsch in 1997, Norris despairs over, quote, "yet another bout of wacky metaphysical extravagance," end quote. So these sentiments are representative of off-the-cuff remarks against EQM uttered in casual settings, but there's a notable absence of argumentation in the literature. This is unfortunate. The objection, whatever it is, underlying these sentiments is sufficiently strong to dissuade some non-Everettians from viewing EQM as viable. Yet, it's weak enough that Everettians have historically simply brushed it aside. There are multiple versions of this objection, as I discuss. In their haste, Everettians have failed to recognize the versions of the objection that are not immediately dismissible. This is a shame. It seems to me that Everettians only stand to benefit from engagement with the more compelling versions of the objection. The remainder of the talk will proceed as follows. I'll start with a discussion of incredulous stare-style arguments that have been leveraged against EQM. Next, I'll pause to examine the state of play before assessing which of these norms are justified. And finally, I'll forecast a possible move available to the Everettian wishing to improve their ontological commitments. So let's begin. Though neither David Wallace nor I have been able to locate this exact sentence, David Lewis supposedly wrote, quote, "I don't know how to refute the incredulous stare." So Wallace thus begins the first interlude of his book, recounting an imagined dialogue between himself, a proponent of the many worlds interpretation of EQM, and a critic thereof. Unfortunately, this appears to be the most thorough and explicit treatment of this oft-cited objection to EQM by an Everettian. So from this exchange, I've reconstructed the objection as follows. Occam's razor demands that we not multiply our ontological commitments beyond what is strictly necessary. We ought to adopt Occam's razor. EQM entails a multitude of worlds, and this multitude of worlds are not necessary. So by 1, 3, and 4, EQM violates Occam's razor, and we ought not accept EQM. So Wallace initially disputes premise 4. The multitude of worlds, he argues, are necessary. The sense in which these worlds are necessary, though, depends on whether we take EQM to be true, and this obviously shouldn't be compelling to anyone who doesn't think EQM is true. John Bell agrees with me. Quote, "The Everett theory is simply the pilot wave theory without trajectories. No, it seems to me that the multiplication of universes is extravagant and serves no real purpose in the theory, and can simply be dropped without repercussions." So this could spell some trouble for the Everettian. As becomes evidenced through the dialogue, though, the disagreement between Wallace and his imagined interlocutor rests on diverging interpretations of what sorts of unnecessary ontological commitments are pernicious according to Occam's razor. Here's Wallace. Quote, "We don't tend to assume that cosmological theories are a priori more or less likely to be true according to how many galaxies they postulate. Generally, in physics, we try to keep our number of postulates and the complexity of our theories as low as possible," end quote. So from Wallace's utterance, we can extract two possible norms. First, If Wallace's imagined critic is correct, Occam's razor tells us that we ought to prefer theories that commit us to fewer objects. I'm inclined to agree with Wallace here, though. It doesn't seem to me that we should think that theories are more or less likely to be true just because they commit us to the existence of some number of galaxies. Everettian worlds, though, are a bit different from galaxies because they're not observable. Wallace anticipates this concern and dismisses it, insisting that our best theory, EQM, of course, tells us why they're not observable, and further, that if we were properly situated in the multiverse, they would be. There are two ways to interpret this properly situated in the multiverse bit. So the first way is to see just some other world, we'd have to be an inhabitant of that other world. And two, to observe many worlds concurrently, we'd have to occupy a quite different sort of perspective altogether, a sort of God's eye view. The former counterfactual reading is trivially true, but for that reason, it wouldn't solve the problem of observability for the Everettian. The latter, on the other hand, makes very little sense for inhabitants of the decoherent branching structure, so I don't find it especially compelling. Fortunately, however, this all helps sharpen the ontic-comparison formulation of the objection. It's not merely that we ought to prefer theories that have smaller ontological commitments, but rather that we ought to prefer theories with more modest commitments to unobservable objects, all else being equal. So, put more precisely, for any two theories, TA and TB, that have identical explanatory and predictive power, we ought to prefer the theory with more modest commitments to unobservable objects. I'll call this the comparative ontic abundance norm. By contrast, Wallace advocates a norm concerned with postulate abundance. For any two theories, TA and TB, that have identical explanatory and predictive power, we ought to prefer the theory with a more economical set of postulates. When I say more economical set of postulates, I mean to reference both the number of postulates and the overall complexity of them. Wallace is quick to dismiss the ontic abundance norm, unsurprisingly, claiming, if you say that Occam's razor rules out the Everett interpretation, you're not really making just one more application of a tried and tested philosophical principle. You're appealing to a new principle, that we should reject theories according to which the universe exceeds some threshold size, and that principle doesn't have any independent motivation. So whether we should outright reject theories on the basis of the size of the universe that the theory commits us to is something different from comparative ontic abundance. This norm contains an appeal to an absolute criterion. I'll call this the absolute ontic abundance norm. We ought to accept any theory T if and only if T ontologically commits us to fewer than n unobservable objects. And of course, there's an analogous postulate abundance norm, which tells us that we ought to accept any theory T only if T's set of postulates meets some threshold level of economy. So at first glance, we might be tempted to follow Wallace and dismiss the absolute abundance norms outright, but I think this would be a mistake. Here's how these norms could function in practice. So consider two different scales for the application of List norms. First, you could think about inter-community judgments. So in these contexts, discussions should share some prior ontological commitments. So for example, these judgments might have been made at the 2012 Many Worlds Interpretation Conference in Tel Aviv, where the focus of the conference was the question over why it's not the case that everyone's already an Everettian. And two, for inter-community judgments. In contrast to the previous context, this is much more global. So for instance, these sort of judgments might have taken place at the 1962 conference on the foundations of quantum mechanics at Xavier University. Okay. In the local cases of application, individual researchers and local research communities might reflect and come to believe that their personal or community sensibilities around postulate or ontic abundance have been violated. In such cases, they would be motivated to seek a competitor theory and then subsequently employ the appropriate comparative norm or norms to help adjudicate between the two options. Now, in cases of global application, the comparative norms reign supreme. This is where we might, for instance, hold up our best Bohmian and Everettian ontologies and select the better option. The problem, as we saw in Wallace's dialogue, is that Everettians and non-Everettians, such as perhaps Bohmians, prioritize different values in theory choice. And it's not obvious to me that either group is correct. There's no clear way to weigh these competing values against one another. So even if they're justified, arguments from parsimony alone can neither condemn nor vindicate EQM. So now I'll discuss an alternate sort of incredulous stare argument against EQM. The nature of reality, according to EQM, is unexpected. This is the gist of the sort of repulsion that Emery sharpens into what she calls the minimal divergence norm. Quote, insofar as we have two or more empirically adequate scientific theories, two theories that both accurately predict the phenomena that we observe, we ought to choose the one that minimizes the difference between the way the theory says the world is and the way the world appears to be. So if we think that the best way to do metaphysics is to first look to our best scientific theories, which seems reasonable to me, then we should take this approach to metaphysical theory choice. We perceive the world as being made up of macroscopic classical objects such as tables and chairs and the like. So for any remotely adequate quantum theory, we must be able to tell a story about why we perceive the world as we do. And the simpler the theory, the better. This spells trouble for EQM. It doesn't exactly say that the world is wildly different from the way it appears to be, but instead that there is way more to the world than there appears to be. But there's a small problem with the minimal divergence norm. There's no unique way that the world appears to be. This certainly varies agent to agent, and it's theory-laden. All observations are. So I want to sharpen the minimal divergence norm, at least for the sake of choosing between different quantum ontologies, to avoid the problems associated with the theory-ladenness of perception. Instead of comparing ontology according to such and such theory to the manifest image, why not compare it to the ontology according to classical mechanics? Three worries arise immediately. First, classical mechanics makes use of all sorts of theoretical entities that are unobservable, such as point particles and fields that are decidedly not part of the manifest image. But in response, classical mechanics is itself an idealization. Detecting the real-world counterparts to the objects of the theory should be sufficient to dissolve this worry. We can often readily observe the sorts of systems that we use classical mechanics to model. There's an easy story to tell linking classical mechanics to the manifest image. For those who deeply value a primitive ontology, leaning on classical mechanics as an intermediate step can help them formalize their account. Okay, here's the second concern. Of all the available theories, why look to ontology according to quantum mechanics as a guide to our metaphysical theory choice? After all, classical mechanics could have very easily been something else. This also doesn't especially worry me. Classical mechanics has a really obvious primitive ontology, and it's the predecessor theory to quantum mechanics. So third, one might worry that there's no singular classical mechanics. In response, for concerns relating to the divergence between their ontic commitments and those of the Everettian, the differences between the various formulations of classical mechanics are probably negligible. It's in our best interest to make modest modifications to our ontological commitments, to help us avoid taking on unnecessary ontic commitments. This is not to say that our ontic commitments will not shift as our best scientific theories evolve, but we should just be a bit conservative about these matters. So with those issues dealt with, we find ourselves with two additional norms for theory choice. The first is absolute classical divergence. We ought to accept some theory T only if the difference between the way T says the world is and the way classical mechanics says the world is falls beneath some threshold amount. And the comparative classical divergence norm. For any two theories, TA and TB, that have identical explanatory and predictive power, we ought to prefer the theory that minimizes the difference between the way the theory says the world is and the way classical mechanics says the world is. So now we have a nice little taxonomy of simplicity considerations. So I'll quite briefly review the state of play. One, it's difficult to know how to definitively apply comparative ontic abundance and comparative postulate abundance to either condemn or vindicate many worlds' ontologies. And two, and I'll note, this is probably why there's been a breakdown in communication between Everettians and their critics. And it's not totally clear that we should accept any of these norms. So are any of them justified? Let's start with comparative postulate abundance and compare it to the analogous norm in scientific inquiry. After all, scientists and metaphysicians are interested in what the world is like, so it'd be unsurprising if they were to share some methodologies. So scientific theories with simpler sets of postulates stand a stronger chance of confirmation. They're easier to work with. But as Willard argues, there's no real sense of confirmation in metaphysics. But historically in science, there's a pattern of simpler theories replacing complex theories as science progresses. For example, we saw circular orbits plus epicycles on epicycles replaced with elliptical orbits. But again, there's no similar sense of progress in metaphysics. So many of us find simplicity, a la postulate abundance, aesthetically pleasing, but it lacks a normative punch. At best, we could adopt this norm in order to attract others to adopt and work on our theory of choice. So perhaps there are good practical reasons to adopt the postulate abundance norms. I'm afraid that the ontic abundance norms don't fare much better. So again, it's reasonable to think that if some scientific theory TA is identical to some other theory TB, except for some bonus ontological commitments to entities that play no explanatory role, we should favor TB because it's easier to confirm. In the case of metaphysics, however, there is once again no relevant notion of confirmation. So it's not obvious that this norm should apply either for metaphysical theory choice. But maybe this is a good way to attract colleagues. Let's move on to the classical divergence norms. So Emery observes that historically we have tended to prefer metaphysical theses that do not wildly contradict our common sense or our best scientific theories. But even if we have historical evidence of this, this is a description of our preferences, and there's no reason to think that the future will be like the past, or no strong reason. So should we continue to prefer such theories? Emery argues that we should, with an inductive argument. Basically, it's worked in the past, it'll probably continue to work in the future. But I'm not sure there's any reason to think that this is truth tracking. But there might be other reasons to adopt the classical divergence norms. Perhaps this sort of norm can help research communities organize themselves and conduct their inquiry more carefully. Even though there's no real sense in which there's global progress in metaphysics, individual research communities build on existent work over time. So I'm going to make a proposal for a way that metaphysical inquiry could be guided over time by drawing an analogy to Lakatosh's methodology of scientific research programs. Now, on his account, the identity conditions for any given scientific community consists of the hardcore, the immutable identity conditions for each community. Surrounding the hardcore is a protective belt that involves peripheral commitments that can change or evolve over time. So this account describes research communities and tells us when they are degenerating, when the hardcore begins to erode. And I think research communities in naturalistic metaphysics also have similar hardcores. But in these cases, I want to say that the hardcore consists of the ontic commitments of the predecessor theory for any particular research community. For those interested in quantum ontology, the relevant predecessor theory is classical mechanics. This may initially seem like a weird choice, but different quantum theories have different ontic commitments, even though they're interested in the same sorts of questions. I think that the so-called protective belt can be carved up into regions of whatever the desired coarse graining is, and that by minimizing the distance between the set of ontic commitments of the shared predecessor theory and the new metaphysical theories, research communities will avoid committing themselves to unnecessarily radical revisions to our ontological commitments. So in order to put forward their best ontic proposals, sub-communities should work to minimize classical divergence while preserving their unique commitments before invoking the comparative classical divergence norm. It's not that this norm helps us select theories that are more likely to be capital T true, or at least I don't want to argue that right now. But this norm helps us more carefully explore possibility space within research programs. Okay, what's the Everettian to do? So according to the classical divergence norms, EQM is problematic because it seems to commit us to a many worlds ontology. Classical mechanics, on the other hand, does no such thing. So let's look at a quick formalization of the argument. This mirrors what I had projected earlier, so I'm just going to not read it out. And I'll say that if it's possible for the Everettian to make do without the commitment to many worlds, this would be the ideal place to minimize classical divergence. Thanks so much.
Thank you for the wonderful talk. We have time for some questions.
Yeah, thank you. Nothing that I disagree about.
Oh, that's
It was
good.
just like I'm very curious, like how ingenious arguments people can create to defend it and try to make even Meniver's interpretation somehow plausible. So it's you presented some incredible examples, so that somebody just has started to think in some way, then they just defend it until the end, just invent some mechanism that makes it work.
Yeah, I think that's why parsimony arguments are not super promising for this. This whole project arose out of an argument I was having with Al Wilson over whose respective ontology of EQM was like more parsimonious, and we both felt very strongly about it. So,
Since there's time, I'll push you a bit on something. You said that the ontology of classical mechanics is sort of trivial or straightforward or something like that. And I don't think that's the case, because you can formulate classical mechanics in many different empirically equivalent ways. And if you read out their ontology, they're quite different. So if you're doing Lagrangian mechanics, you don't have forces, for instance, at all. So would you like to comment?
yeah, my thought is that although there are many different ways we could interpret classical mechanics, there are many different formulations of it. The differences between these are going to be like microscopic compared to the differences between classical ontology according to classical mechanics and ontology according to, i.e., Bohmian mechanics, or a really nice formulation of EQM that avoids this problem.
Thanks.
Yeah.
Any more questions?
So I was always curious, is this idea of many worlds, are there differences in how people view them? Are they some people consider them to be real and actually exist, and some people think that they are more like idealizations?
Idealizations.
Or some kind of ideal Platonic things that
Yeah.
help in the interpretation?
I think most Everettians are committed to the other branches being real and concrete. But notably, Christina Conroy has this really cool account called Everettian Actualism, where the other branches enjoy the same status as numbers, so they're mere abstracta. But many Everettians condemn that as like not genuine Everettianism, because Hugh Everett said there's no reason to suppose that like any world is more special than any other in terms of concreteness. Did that answer your question? Yeah.
Thank you. Our time is up, unfortunately. Let's thank the speaker once more.